Alright, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Very good morning to all. Okay, so I hope today, this
Waalaikumsalam,
week,
Madam.
salam, thank you for responding. So, this week is already our 9th week, okay, for this semester. So we are, in terms of our syllabus and all, we are kind of like on track. Okay, on track, by means that, we don't have any issue of, delay in terms of our course, syllabus, and so on. Okay, and I've been told that instead of 14 weeks, actually we have like, I think around 22 weeks. Okay, so we have more than enough ample of time for us to cover our topic for this course. So I just want to let you guys know that I have decided. Okay, where is it? Mana tadi? Yeah, I share first our screen. Okay. Okay, so maybe you can scan the attendance for today. All right, just want to inform you guys. So for our course, we have on 3 hours, right? Every week we have 2 hours lecture and also another 1 hour lecture. Okay, so two different times. So basically, what I have decided, I will only give lecture for 2 hours. Means that we're gonna have this online interactive lecture only for the 2 hour session. Okay, and another 1 hour. Okay, another 1 hour, I will open up for any kind of discussion. I will not proceed with any lecture, okay, to cover our topic. But I will still be online, okay, I will still be online, but we're gonna spend more on like discussion. Okay, so if you have any problem in terms of your assessment or the topic that you don't understand, okay, or anything at all, so I'll use this time. Okay, so I will be online. Okay, we can talk about anything. All right, regardless anything. If you don't have anything to ask about the course, you can ask me anything about civil engineering in a way, maybe opinion, maybe like issues, current issues, maybe anything that we can talk about. Okay, anything that, if you don't have any, because I found that when there are some question when you ask through WhatsApp, I didn't really, it doesn't satisfy me in terms of answering your answer, because some of the thing require explanation, but I couldn't do the explanation through WhatsApp because, with the equation and all, what the most I could do is just I will circle it and then just type, with the limited words, or to record voice. Didn't thought about that, but somehow or other, I think maybe through the online will be clearer, the issue or any problems that you have. Okay, so yeah, that's one thing that I want to let you guys know. So we will have 2 hours online like this in terms of covering our topic, okay, our lecture. So another 1 hour, which is your session, will be on your session is supposed to be yesterday, right? 1 hour kan? Okay, so we kind of like missed that already, but it's okay. Then we have like a next week, okay, for the 1 hour. So at least, because I found that when I do the 1 hour, 2 hours, so some of you, the students or the group, sometimes a bit lag, others some a bit faster and so on because of the time. Okay, different time too. So I hope with this, then I can, be more consistent in terms of deliver the lecture to you. And I think at least it will help you, it will ease you a bit lah. Okay, because there are some complaints from the students, to our faculties or to UiTM as a whole, saying that you are stressed because of the learning environment is not conducive at home and all. So the online learning is very stressful and so on kan. So I've been thinking about it. So I think probably this is one way that I could help you guys. Okay, maybe ease a bit. So instead of having 3 hours straight for our lecture, we're gonna have only 2 hours. Okay, we are gonna have 2 hours, so the 1 hour lecture I will be still online, but we gonna have like more open discussion lah about anything. Okay, alright, boleh, Syafika?
Boleh, madam.
Boleh ya? Kan ceria.
Boleh, madam.
Tu gambar, kalau ada gambar lagi ceria. Okay, Syafika ada gambar, I can see her. Okay, alright. So okay, let us proceed then. Okay, shall we? Bismillahirrahmanirrahim. So ultimate shear strength. So today topic will be about ultimate shear strength, which is another typical failure of a beam that we have to check for at ultimate limit state. Okay, after we design our pre-stress. So last week we have gone through the what we call as ultimate bending moment. Okay, we have checked in terms of bending moment. So is it sufficient or not? Is it require additional reinforcement or not? Okay, is it how many reinforcement that you need to add? Is it your pre-stress tendon, is it sufficient for the moment or not? So we have checked that all that we have checked. Okay, so at that point, it kind of like in terms of moment, it's already covered. So now we go for shear, because we always know in terms of design, we always gonna have two what we call that two main failure. We always gonna deal with these two main failure, which is one will be the moment failure, another one will be shear failure. So we have to always ensure that when you design our specimen, it must be sufficient against moment, and it must also be sufficient against shear. Okay, because we want to design something that will not fail. So how to design something that is not gonna fail is to cater the failure. All right, to cater the failure by calculating how much you need to counter the failure from happening. Okay, so the main outcome for this topic will be at the end of this lesson, students should be able to determine the ultimate shear capacity of the pre-stressed concrete beam. Okay, all right. Okay. Sekejap. Wait only. Because just now it's already the something. Okay, so shear in pre-stressed concrete is considered as ultimate limit state. I think everyone knows about it already, right? So the behavior of PAC beam at failure in shear is distinctly different from their behavior in flexure. Alright, so in terms of failure, shear is of course is different from flexure. What is flexure is when the failure of your beam is caused by moment or bending. Okay, so the beam failed abruptly without sufficient warning. Alright, so what happened comparison between shear and bending moment? So when bending moment, the failure happened, you'll be able to see the beam is actually bent. Okay, and slowly until it fails. Okay, but somehow rather when you have shear, normally it will appear only like a small crack like that, and then of course, and then suddenly when the beam fail to cater the load from shear, then it will like abruptly it will be failing. It will like cracking, and there will be a big gap and it's already like collapsed. Okay, and the diagonal crack that develop are considerably wider than the flexural crack. Okay, so shear crack is normally diagonal direction. It's not like straight direction. Normally it will be diagonal. So diagonal crack is normally considered as shear failure. So shear forces results in shear stress. Okay, of course, the forces coming from the stress. So such a stress can result in principal tensile stresses at the critical section, which can exceed the tensile strength of the concrete. Okay, all right. So when the tensile strength of concrete is exceeded, crack will form. Okay, of course, when the strength capacity of a beam exceeded, then of course the failure will happen, which is in this case crack. So the response of pre-stressed concrete member in resisting shear is similar to reinforced concrete member, except additional effect of the compression due to pre-tension, pre-stressing force need to be taken into account. Okay, so additional effect of the compression, okay, need to be taken into account. So variable strut inclination method is used, okay, of shear design, which is what being used recommended by EC2, okay, to compute the shear capacity for pre-stressed concrete design. Okay, because we know that, you know, when the crack happen for shear is always inclined, so we that's why we use this method called variable strut inclination. So in calculating design ultimate shear force, which is VED, right? Which is what you calculate from your, what you call, from your self weight, from your loading. It is permissible to take into account the vertical component of force in any inclined tendon, which will tend to act in direction that resists shear. Okay, so that's one. You know, we have to ensure. All right, so looking at this, okay, just to go through this before we go in any further. All right, anyone after do you, what you call that, for concrete beam, for reinforced for, you know, typical beam, okay, where will be the location of shear failure to happen? Anyone, may I know anyone answer before I call name? Ada siapa yang know how, where is the normally shear failure will appear? Where will always the shear failure appear? The location in a beam. Yeah, Fitri.
Dekat support.
Kat support. Jacqueline?
Middle.
Yeah.
At the middle.
In the middle.
Uh,
Anyone else? Aina? Maybe? Middle, between support and at the mid span. Okay. All right. You guys also have to aware when you design, okay, when you design your structure member. So it's not about your capability in terms of answering your, what we call that, at the mid span. Okay. It's not about your capability of you to solve question or to answer past years, you know, or I know that's what you've been doing, you know, I know that's what you've been trained, because you need to answer exam question, final exam question. Okay, so when you answer question, normally all the parameter given, so you only like have to design within the parameter and so on, whatever information, because we have kind of like a constraint in terms of, you know, in answering question, right, in the examples or in your final past year's question and all. But one thing you also have to remember is design, for design courses, or actually it's not only design courses, any courses, you know, it can be geotech, it can be water, it can be any, you know, any course in civil engineering. So engineering is actually is quite straightforward course, you know, it's very logic sense course, I would say, because there's nothing magic in this course. Okay, why I say magic means there's no such thing as suddenly happen without any reason. Everything happens, or any behavior happens, there must be a reason behind it. There must be why it happened. It's not like suddenly it must be like that. No. Right? You say that you're being told like that, you must find what will be the answer. The important thing is you have to understand the behavior of the thing. And when you understand the behavior, and then you understand the concept of behind the design principle, so whatever problems thrown to you, you can solve it. Because you have to remember, when you work outside there, okay, when you start to work, you know, dealing with the actual problem, real problem, the problem will not be like what you get from your test or from your final exam or from your example, where you can always, like, you know, refer back to the example, how it's being solved, you know, with this, if the this parameter given, you solve it like this. When this parameter given, you solve it like this. You know, that's how you always do, right? When you want to prepare yourself for your final exam. But you also have to also prepare yourself, you know, in a way, when you don't understand anything, in terms of your any course, you have to figure it out. What are the science explanation? What are the logical explanation behind the principle? Okay, all right. It's because it's very important. By looking at your answer, like a simple question just now, I will say that majority of you are still not sure in terms of the sense, the logical sense, behavior of a beam. The simple structure is a beam. We're not talking about trusses ke column lagi. We are just talking a beam, a very common structure, kan? Okay, so you're still not clear about it. All right, because you can, some of you cannot give me the right answer. Okay, so it shows me that. All right, so and it's quite it's troublesome for me to know to know this, because you guys are about to graduate, kan? So please, I mean, any course, this is the time where you try to understand, polish your understanding in terms of the principle, how it behave, ask your lecturer, try to find out more about the thing. Sometimes a simple word like, for example, like this, the shear. Okay, if you cannot elaborate it in terms of logical sense that you understand, then it's a problem. Okay, so let's take a look. My question is simple. Where is the failure? How to know where is the failure? Okay, sorry, talking too much without water. Dry my throat a bit. Okay, all right. So the word shear, all right, so you have to kind of like understand as well, because it's not just about to know where is the failure, but you also have to understand why it happened. Okay, how it happened. Okay, for example, let's take a look at this. We have one simply supported beam. Okay, this is very, very common, simple beam. We have a look at this. We have a load, right? A UDL load. Okay, what we do, normally what we do, the very first thing that we do when we analyze any structural beam is we come up with the bending moment, correct? So we know it's something like this. Okay, and this is your bending moment diagram. So we know that bending moment is 0, 0 at support, and there's a maximum moment is at the center. So when the failure of a beam, when it caused by the bending moment, okay, we call it as flexural failure. Okay, we call it as flexural failure. So another diagram that we always draw, we always refer to will be your shear. Okay, from this simple diagram also give you so much information for your understanding. Okay, you see that maximum here, then the maximum failure will happen. This is the maximum. The maximum capacity is all taken from this value. Okay, this is for moment. The same thing for the shear. All right, the maximum happen here. The maximum happen here. This is the maximum shear. Okay, so that's why normally for shear, failure will happen near to the support. Why? The behavior of the shear is always be like this. This is a shear because you have two different what you call position or direction of a load applied. You have one is going up, one is going down. Okay, so in our case, we have it one down is going to be the load applied, and then one up will be the support. So theoretically, what we stand for is we say that whenever load is applied to a beam, it will be supported by a support. Okay, where the support is supposed to be holding this beam. Okay, so that the beam will not be like deflected in one direction. If say that the support here is not strong enough, then the load is like bigger than the support, then of course this beam will deflect. Correct? Means it's not well supported. Okay, but what will happen if say that the beam itself, is kind of like, you have like one is straw, both are not in the sufficient condition, and then in terms of the load applied and also the support, then it will cause the shear to happen. Okay, the shear to happen when the material is also not compatible with the load applied and also not compatible with the support applied, the support used. Okay, so that is where in this direction, this position is where normally you will see the what you call the shear failure will happen. Okay, a simple what you call diagram like this, okay, able to explain the behavior of one span of a beam. Okay, this is very basic understanding that you should be able to explain. Okay, especially considering you almost graduate and all. Okay, when you design, you must be, you must always counter these issues. Okay, because we know beam will fail in terms of moment, will fail in terms of shear. Okay, when you do your RC design also, this is our two main failure issues that covered in your RC as well. Okay, so the same things goes for your pre-stress. Okay, because it's still it's still a beam with additional tendon, of course. All right, so am I clear? Did I make myself clear? Boleh, Farisha?
Boleh.
Boleh ya? So
Madam.
okay, so those please take note. Okay, I think it's not too late. Okay, you can always discuss about understanding and all. So I'm happy to try and make you understand further, because the most important, because when you don't understand the principle, when you don't understand the cause, you don't understand how it behave really, and then you just understand how to use the formula, which formula to use and so on. You just only know that. So when when you are solving a real problem, then you will have problem. Okay, you have issues. Okay, because all problems normally are very unique. You need a strong fundamental background to really understand and solve the problems. Okay, all right, let's take a look next. Okay, we have covered this. Okay, all right, so in a way this is like the shear force that we consider. Okay, when we design for your shear. Okay, we take account into terms of vertical component of force due to inclined tendons. Okay, we consider it inclined. Where pre-stressing force, we multiply with the partial factor of safety, which is 0.9 as usual. So this increases shear resistance considerably by enhancing the shear capacity, which is the shear resistance. Okay, so we have few conditions whereby you have resistance C, where this one is without shear reinforcement. So we have resistance S, which is which can sustain by yielding shear reinforcement, and also you have shear resistance maximum, where design value of the maximum shear force can be sustained by the member, limiting by crushing of the compression strut. Okay, that's one thing. And then we also have what we call the inclined chord symbol, where you have the VCC, which is this is the component of the compression area, and then the VTD or shear TD, we have tensile force area. So you have this direction for above the neutral axis, and then also below the neutral axis, which is the tension. Okay, so this is the figure where you consider the inclined chord, because we always for shear is a bit different from moment, because moment when you apply load, okay, your beam will bend like this. Okay, it's common to see that your crack will appear like straight, like vertical line. So whatever applied in this direction, that's why the calculation is very straightforward. So whatever applied in the vertical direction, you just measure and then you put, you calculate it, and then you would know what will be your moment maximum or failure. But for shear, Okay, the thing is a bit different because you have two different forces applied, and then the failure will happen something like this. The crack is inclined. Okay, so you can the relationship between the failure, which is the crack in this case, and the direction of the force, okay, and also the support or the load that applied, it's not, it cannot be like relate it relatively, you know, it cannot be related directly as you relate the failure and also the load applied for moment calculation. Okay, so that's why you have to consider the direction or the inclination of the crack. Okay, when the shear happens. Okay, all right, for example, like this figure you can see. Okay, so this figure is very clear, right? I really like this figure because it shows the location of each failure that happened in one particular beam. So this beam is actually, it's not simply supported beam, it's a continuous beam, right? So it's very common when you have like, you know, your beam looks something like this, right? For your moment. So you have hogging here, you have positive sagging there. Okay, and the same things with your, what we call that, with your shear. Cracking in pre-stressed concrete beam at ultimate load depends on the local magnitudes of moment and shear. Alright, so the crack always be the initial cause of a failure, initial sign of a failure. So the more crack happens, so then the worst failure will happen to the beam. Okay, so here let's take a look at the region A. Right, you take a look at the region A, where you will see the vertical line here, somewhere here, something like that. So this is where you call it as a flexural crack. Flexural crack means that you have your ultimate limit state in flexure, means the failure or the crack is caused mainly solely by moment only. Okay, so that is where we initiate it, or we call it as region A, means located at region A. Okay, so this is where it's called crack section lah, at region B. Say that it's a region B. Region B is located here. You will see a slide like, you know, what we call a diagonal direction of the crack. So at region B, we say that it acts as a flexure shear crack. Okay, the shear crack, flexure shear crack means that the moment is kind of like what we call not high, and also the shear also not high, it's not dominant in this case. For region A, moment is dominant. That's why when you divide moment divide by V, then you get the ratio of this is very high, you know, big numbers, because the moment is bigger than the V. But when you have a flexural shear crack, you have both value are moderate, means like more or less the same, or not really the same, but there's no like entity that is big, higher or lower. Okay, so both are moderate. So we call it as flexural shear crack. So it happens in like in a flexural what we call domain. Okay, and we have also the third region where we call it as a C region, like this, and we call it as a web shear crack. Okay, web shear crack is whereby you have M is very low and V is higher than the M, means the shear is higher than the moment. So we call this as an crack section. Okay, for this region C. So this where you have C and then you have C here, and you will see that this one is you have vertical, you know, like below the we call that what we call near the underneath of the beam section, and then this one is above. So it actually act as what you have for your moment, moment for your sag and also moment for your hop. Okay, all right. So this is the explanation of each typical. Let's just go through it as what I said, aside what we have explained before. So in region where the moment is large, shear is small. Okay, like we have like M over V just now, and then we have its what we call higher kan, the value. So the moment is higher and the shear is small. So vertical flexural crack appear after the normal tensile stress in the extreme concrete fiber exceed the tensile strength of the concrete. Okay, so we have it here. So this is the region A. So this is why we call this as a region A. So at this point, normal tensile stress in the extreme concrete exceeds the tensile strength of the concrete. So that's why you have the crack up here. Okay. And next we have where both, for this is at region B. So both moment, as we say, and the shear force are relatively large. Could be moderate, it could be large. It's more or less the same. Okay, so flexural crack with which are vertical at the extreme fiber become inclined as they extend deeper into the beam, owing to the presence of shear stresses in the beam web. Okay, so that's what actually happened that caused the inclination of the crack at beam region. Okay, so these inclined cracks, which are often quite flat in a pre-stressed beam, are called flexure shear crack. So it's like a combination of two failures, which is caused by the moment and also caused by the shear. We call it flexure shear crack. So I'll design it as a B. You can see it here. Okay, and if adequate shear reinforcement is not provided, then the flexure shear crack may lead to so-called as shear compression failure. Okay, so when you see the crack, so we always, when you design, want to avoid the failure from happening. If we know that the failure will happen, so of course we will provide reinforcement, so then it will avoid it from happening. So if you don't provide, then that's where you know the failure will happen. So in this case, if you don't provide adequate shear reinforcement, then what we call as shear compression failure will happen. So in which the area of the concrete in compression above the advancing inclined crack is so reduced as to be no longer adequate to carry compression force resulting from pressure. Okay, so that is actually what happened in B region. Okay, so second type of inclined crack, so sometimes occur in the web of the pre-stressed beam. So what you call the web is where you have like something like this, right? It happens like in the middle of the section. Okay, normally like probably thinner width and so on. So a second type of inclined crack sometimes occur in the web, okay, of the pre-stressed beam in the region where moment is small. Okay, moment is small and shear is large. Alright, so in the such crack we call it as a type C, adjacent to the continuous support, okay, near the point of contraflexion, okay, in the figure. Alright, so that's what we commonly see. So normally it will be near to the what we call to the discontinuous support. Okay, so in such location, high principal stress, what happened actually? High principal tensile stress may cause inclined crack in the mid-depth region of the beam before flexural cracking occurs in the extreme fiber. Okay, so these cracks are known as web shear crack. We call it as web shear crack and occur most often in beams with relatively thin webs. Okay, normally because it's very common for pre-stressed beams. Okay, we have like a thin web because we have we rarely use a rectangular solid beam. Okay, we rarely use rectangular solid beam because we have to go back to why we use pre-stress in our beam. We use pre-stress in our beam so that we can have more smaller sections, right? We want to optimize the section because once we reduce the section of a pre-stressed beam, we can reduce the weight, okay, of your concrete. Okay, so it's very common for pre-stress. We have like a T section, which is your web is thinner than the flange. Okay, you could have like probably I section. Okay, you could also have like a hollow section. Okay, you could also have a U section. It's not like this, like U section normally prefer like this kan. Okay, all right. So that's about it. Okay, so how about the effect of pre-stressing in shear? Because we know pre-stressing in moment, okay, sometimes it helps in terms of, it contributes in terms of you do not need any additional reinforcement to cater for your moment because it's already catered for your by your tendon. But how about your pre-stressing in shear? Okay, so longitudinal compression introduced by pre-stress delays. Okay, it will delays the formation of each of the crack types shown previously. Okay, it doesn't say it will replace, but it kind of like delays. So the effect of pre-stress on the formation and direction of inclined crack can be seen by examining the stress acting on a small element located at the centroidal axis of the uncracked beam. So you want to know the effect, then you can examine the stresses for the uncracked beam. So how you do that is by constructing a simple Mohr circle construction. Okay, because we want to know what will be the, where is the principal stress and the direction. Okay, because we're talking about diagonal crack. Diagonal crack with a vertical load applied. So you want to know how it kind of like, the relationship or the interaction between these two. Okay, so when the pre-stress is 0, okay, say that is 0, okay, and the stress 1 is equal to the shear stress, which act at 45 degrees, something like this, okay, to the beam axis. If diagonal cracking occurs, it will perpendicular to the principal tensile stress, which is at 45 degrees to the beam axis, something like this. Okay, it will be about 45 degrees. Okay, so when the pre-stress is not 0, okay, that is when the pre-stress is 0. So when the pre-stress is not 0, so the normal compressive stress, which is the stress, reduces the principal tension of stress 1, this stress 1. We consider it as in one direction, okay? The angle between the principal stress direction and the beam axis increases. So consequently, if cracking occurs, the incline will be flatter. So it will kind of like not necessarily has to be like 45 degrees, so it will be lesser than 45 degrees, getting flatter, like maybe 22 degrees and so on. So pre-stress therefore improve the effectiveness of any transverse reinforcement or stirrup that may be used to increase the shear strength of a beam. Okay, so well, in a way, the tendon itself, if you look into the relationship of your Mohr circle, where your principal stress and so on, so in a way, the tendon itself will improve the effectiveness of the transverse reinforcement because it helps in terms of flatten the angle, the what you call that, the angle of the crack. Okay, so it kind of like increase the shear strength of a beam as well. So with pre-stress causing the inclined crack to be flatter, okay, a large number of vertical stirrup legs are crossed by the crack and consequently a large tensile force can be carried across. Okay, so you can provide a large number lah. You can provide what you call that, vertical stirrup. And when the principal tensile stress, which is stress 1, reach the tensile strength of concrete, so cracking occurs and the crack form in the direction of perpendicular to the direction of stress 1. Okay, because you have to ensure that whenever you provide your your shear reinforcement, okay, your against the crack, so it has to be like always, because it's like you want to avoid it from happen, so of course you want to provide something that opposite it, or to counter it, okay, in that particular direction. Okay, so that's more about the principle behavior. So now we take a look of how we wanna check our shear capacity. Okay, how we wanna calculate it. Okay, there are three main conditions in terms of you wanna consider or you wanna design your shear capacity for your beam, for your pre-stress beam. Okay, first condition will be we want to assume the condition of your beam. Okay, the section does not require any shear reinforcement. That's number one. Okay, it means that when you do the then you know that your section does not require any shear reinforcement. So that's the first condition. Second condition is the shear strength without shear reinforcement still don't have shear reinforcement for uncracked regions in bending. Means the beam, your beam have load, applied load, okay, have bending, but the bending does not does not cause any crack. Okay, so the shear strength is, of course, when then you don't have any shear reinforcement. But this one is actually very rare happen, but somehow it's a condition that we have to consider. Okay, because normally when you apply load, then of course the bending will have crack. Okay, and third condition will be section that require shear reinforcement. So the section, this is the common lah, where you have you design, then your section require shear reinforcement. Okay, now take a look at the first condition. So the first condition where the section do not require shear reinforcement, whereby your design shear, okay, is lesser than the resistance. Okay, so obviously when your design shear, okay, is lesser than your shear resistance, okay, so of course obviously you do not need any shear reinforcement. So no calculate shear reinforcement is necessary in terms of this condition, but it is necessary to provide minimum shear length. Okay, even though you check, do not need to provide any shear reinforcement, but you have to provide minimum length. Unless for very short span beam or lightly loaded lintel. For example, like it's, the beam is not cause any stability to the structure, any issue to the whole structure, then you do not need to provide any minimum shear length. Okay, lintel is like a small beam actually, but it doesn't carry much load. Okay, so when on the basis of the design shear calculation, no shear reinforcement is required. So minimum shear reinforcement should nevertheless be provided according to clause 9.22. So the minimum shear reinforcement may be omitted, okay, for a member such as like a flat member, where we have like a slab, okay, so like solid rib or hollow core slab, where you have transverse distribution of loads. Okay, you have, because it kind of like, it's scattered, right? It's not concentrate in terms of like a beam, okay, throughout the length. So minimum reinforcement may also be omitted in a member that minor importance, like we say just now, like lintel and so on, which does not contribute to significantly the overall resistance and stability of the structure. So that one you can also omit the minimum shear, no need to provide. So what will be the minimum shear you have to consider is actually you have to calculate what will be the resistance. Okay, the resistance capacity of the shear, and the minimum is this value. Okay, so there are few parameters that you have to take note in terms of these equations. One is the CRDC, which is the resistance, okay, the values. Then next you have the rho 1, and then you have the stress of your tendon. Okay, and we also have the V mean, okay, and also K. So what will be the value? The K, where you can use these equations, okay, for the K. This is for the K value, this K value, okay. Just you take D is your effective. Your rho 1 is where you have the ASI over BW over D, the web of your width. And your ASL is actually your tensile reinforcement area, okay, where you have considered this during. And you have your tendon stress. Okay, you can use this formula, which is must always be lesser than 0.2 SCD. You have to check. And then this is your, what will be your axial force. Okay, your BW is smallest width, okay, of the cross section in the tensile area, which is lower. And the influence maybe ignored. And then the AC is the concrete area, and the VRDC is the shear resistance. Okay, so if you look into this, the CRDC, okay, V mean K1 is normally you use based on the national annex of each country or specific country. So the recommended value of C you can take as 0.18 over gamma C, partial factor of suited for concrete. And also V mean is given in the expression, this expression, okay, where you can calculate this, you know, by putting what will be the K and so on, K1 value. So K1 value, we take it as a 0.15. This is K1 for 0.15. Okay, so I hope you guys are clear in terms of the formula, where's the value coming from. Okay, one by one here. Okay, so this is the simplified, version of what we have, go through it just now. Okay, we have the resistance, okay, with the rho 1, K, and then the stress of the tendon, the gamma P, the K, okay, which is where you calculate your stress of your tendon. Okay, so definition of ASL. So what will be the ASL? So this is your ASL, the area of your tension reinforcement. So this is the point. So this is the area of your ASL, can be taken from this point where your angle is considered. Okay. Okay. Second condition, which is you have uncrack in bending. Okay, so it's a special condition because it's not really like, commonly happen. Okay, so in region of uncracked in bending where the flexural, look here, flexural tensile stress is smaller than this, we call it as a uncracked, okay, uncracked bending. Okay, the shear resistance should be limited by the tensile strength. Shear resistance should be limited by tensile strength of the concrete. So your FCTD is limited value of principal tensile stress. So where your ultimate shear resistance of the uncracked section becomes this. Okay, where you have your I and multiply your BW, which is your width, divide by your S, okay, and you multiply with the square root of SCTD, power of 2, plus with gamma 1, multiply with stress tendon and also FCTD. So and in a way, you calculate your stress of your tendon as what you calculate before. Okay, and you have your FCTD, which is your strength of your concrete. Okay, the tension divided by your partial factor of safety. Your gamma, okay, where you have two values because depending on the method of your pre-stress. So either you are using post-tension or you're using pre-tension. Okay, so it could be equal to 1 or it also could be lesser or equal to 1. Okay, for both conditions. So if you want to take the value, if it's lesser or equal to 1, then you have to calculate your alpha 1. And AY bar in this case is actually equal to the S. So first moment of area above about the neutral axis. For example, that you have here, say that this is your what we call your rectangular beam. So your neutral axis is here. So then you have your Y bar is taken from the top to this, for example. This is your Y bar, and then you have your area, okay, above the neutral axis. Okay, so next will be this is actually more or less the same as simplified before. Okay, this is the simplified term of what we have said, in terms of alpha 1 for post tension and also for pre tension. So for cross section where the width varies over the height, okay, the maximum principal stress may occur on axis other than the centroidal axis. So in such a case, the minimum value of shear resistance should be found by calculating VRDC at various axes in the cross section. So you have to consider all cross section. Okay, because you might have a different different width. For example, like you have here. Okay, so say that you have your neutral axis here. So you have, this is different width. This is also different width. Okay, so you have to recall back in terms of how to calculate it like this. Okay. All right, so you have it centroid, like this. Something like that. Okay, I think you have to recall back how to calculate your shear stress. Okay, this is actually the same. It's not the same, but this is how you calculate your shear stress. Okay, I think in your solid mechanic, if I'm not mistaken. So this is where you're gonna apply. You must be able to use it here. So at uncracked section, a more circle analysis of a beam element which is subjected to a longitudinal compressive stress, which is your FC, and your shear stress, which is your VCO. Okay, your shear stress. Give the principal stress as this. For example, this is a typical VCO location for your, for your stress. This is your stress, your principal stress. So this is your what we call your compression. Okay, so your FT will be equal to this, where you have your VCO into account and also your compression, which is you can rearrange by taking only your shear stress, and you can recalculate what will be your shear stress based on your stress, compression stress, and also tensile stress. So this is where you also calculate your shear stress based on this figure. So that's why I'm saying when you have a different width, for example, like starting from here, different width, here you have different width, so you have this point at this point, at this point, at this point, this point, and this point, and also this point. Okay, I think you can recall back how you want to calculate your shear stress at that point. Okay, so here is the last condition, which is in this condition where you consider that you require the sections, okay, require shear reinforcement, sections that require shear reinforcement. So when you want to consider shear reinforcement, section that require shear reinforcement, we apply the variable strut inclination method, where because we expect that the crack is inclined. Okay, similar design to shear in RC member is no much different from RC. So we consider the angle, okay, the diagonal compressive strut, and excessive compressive stresses should not occur in the diagonal compressive strut, okay, of the assumed thrust, which leads to the compressive failure of the concrete. So the diagonal compressive strut and the angle of theta, maximum shear, will have this formulation that you can refer or you can use. Okay, which is this is the width of your section. Okay, and your Z, and also your V1. This is cotangent theta and tangent theta. Let's take a look one by one, shall we? Okay, so in this case, okay, you have like what we call the strut. This is the method, the variable strut inclination method. Okay, where you estimate what will be the what we call the angle, okay, inclined by the potential crack that will happen in a beam. Okay, and then this is a spacing of each the reinforcement. Okay, and this is the force, the compression, and then this is tension. Okay, so this is the vertical force, right, that will act vertically to the angle of the incline crack. Okay, because that's why you have the V in the representative of cotangent theta and also cotangent alpha, because you have two incline. One is inclined in this direction, and then another one inclined in the other direction. Okay, and you have all the acronym, all the abbreviation, the alpha, the angle, okay, the FTD, which is the tensile force, the compression force, okay, the VW, and also your Z, which is the inner. Alright. So Z can be taken as 0.9D. So in the shear analysis of reinforced concrete without axial force, you can say that your Z is 0.9D equal, because that will be your maximum height for your Z. Okay. Alright. For members with vertical shear reinforcement, shear resistance VRD is the smaller value of this value. Sekejap Alright. Okay. Where am I? Okay, kejap. Kejap break. Kejap, I have something to settle. Kejap. Sorry, you guys. I cannot pay attention as long as I didn't reply the. Okay. Okay, go back to this. Okay, for members with vertical shear reinforcement. Okay. Say because we consider that our what we call. Okay, we consider that our section requires shear reinforcement. Okay, so when we have for a member with a vertical shear reinforcement, our shear resistance is smaller value. Okay, of this where we can calculate this, right, where you consider the ASW divided by the spacing, because this is a very common for what we call when we design shear, when we provide shear reinforcement, even in RC, the value of the area and the spacing, it comes in terms of ratio, right? Because that's why you have the table, right, for your what you call for your link. Okay, and this is why smaller value of this, because this is actually your minimum, and this is where you have your maximum of your shear resistance, where you calculate using your alpha CW. Okay, coefficient taking account the state of the stress compression chord, the BW, which is the width, the Z, the lever arm, which is the V, your strength reduction factors, your FCD, and your cotangent theta and also tangent theta. Okay, so in a way, how you we can also simplify this equation by looking at the next slide. Okay, it's moving. Okay. All right. So the value of V1, all right, which is the reduction factor of your shear just now, and then the alpha CW. So normally it's used in the national annex. Okay. Recommendation of V on the shear one and also the shear, you can see here where you can take it from the BSEN, calculate by considering the concrete strength Okay, and if the design strength, the stress of the shear reinforcement is below 80%. Okay, if the design stress of the shear reinforcement is below the 80% of the characteristic yield stress, which is your FIK, then your V1 may be taken as this. So you have two considerations. One is when your FCK is lesser than equal to 60 MPa, or when your FCK is bigger than 60 MPa. We normally don't say equal lah. Okay, but then you can take your shear reduction factor is 0.6 and also the reduction factor of 0.9 minus with FCK minus 1 over 200. So which is always must be bigger than 0.5. Okay, in a way you have the FCD for your concrete where you take your FCK concrete strength divided by partial factors for the concrete. Okay, so that is more about the V1, or we call it as a what we call a reduction factor. These values, yeah, so the strength reduction factors in shear. For alpha CW, okay, so alpha CW, you take the value based on the value of your stress for your tendon. Okay, so stress your tendon, which is you calculate. Okay, where is the formula just now? Stress tendon, in the beginning you can see the formula of this one. Okay, all right, so the stress tendon you calculate, and okay, the stress tendon you calculate, and then you check either is bigger than 0, is lesser than 0.25 FCD, which is this value, or is bigger than 0.25, lesser than 0.5, bigger than 0.5, and is lesser than 1. Okay, so each of these conditions will have different value of alpha CW. So if say that it's a non-pre-stress, then directly alpha CW is equal to 1. That's why we don't consider alpha CW when you design your system. Okay, but you say that you calculate your tendon is within this class, within this range. So you have to calculate your alpha, which is using this equation. Or if it's a second range, so then you can simply take is equal to 1.25. And if it's in the third range, so then you have to calculate by considering this 2.5. Okay, so hope you are clear in terms of getting your reduction strength factor and also your alpha CW. So here, just what you call that, just to highlight at this point. So CP is the mean compressive stress, okay, measured positive, okay, due to the axial force, which is in this case is the pre-stress force. So this should be obtained by averaging it over the concrete section by taking account of the reinforcement. So the value of stress CP need to be calculated at a distance less than 0.d cotangent theta from the edge of the support. Okay, so that is the distance. Okay, you can consider. Okay, so for limiting value of your cotangent, so cotangent must always be bigger than 1, lesser than 2.5. Okay, why? Because when it's a bigger than 1, means that it's bigger than the theta is 45 degrees. So when it's lesser than 2.5, means it must be lesser than 22 degrees. Okay, it must be bigger than 45, and it must be it must be lesser than 22 degrees. Okay, what you call that? And so your shear maximum, okay, for each of the condition of when your cotangent either is equal to 45 or is either equal to 32 degrees, will differentiate the value of your shear maximum, which is this 0.124, and then this one will become 0.18. Okay, or you could also simplify by considering your theta values, and then you can estimate it either is lesser than 0.45 degrees, or is in this case where it's lesser in 45 degrees for this condition. So there are two conditions to consider in terms of calculating your theta. Okay. All right. What else? Okay. All right. So if say that, because we know for pre-stress there are two possible conditions as well. Okay, we have one with bonded condition, one will be unbonded condition. So when you have bonded, we have grouted, duct, and then if we have unbonded, we have non-grouted. So that is what actually we are dealing. because this also will contribute to different condition of in terms of what will be the nominal web thickness. Okay, these values. Okay, your BW norm. So your web thickness, nominal web thickness, will depends on the condition of your duct. Okay, either it's grouted or it's not grouted. So you have this condition. So you have, your what we call your outer diameter of your duct. Okay, this is your outer diameter of your duct, and then this is like the summation. The most unfavorable level. So what will be the values of your diameter of your duct? Okay, so you have your B, your width of your your section minus with 0.5 multiplied with your diameter. So for the case of your non-grouted, so it's much simpler because instead of 0.5, you minus with 1.2. Okay. So you have this. So you have 1.2. Okay. So vertical shear reinforcement. So this is where we kind of like one provide. So if say that we want to provide the vertical shear reinforcement, okay. So then it is assumed that all the shear force is carried by this reinforcement and contribution of the concrete is neglected. So we can calculate your ratio of your area for your shear. Okay, and then we have to ensure it's bigger than the minimum length required by EC2, which is this one. Okay, and in terms of the core tension, we have two different conditions. We have two, one is 45 degrees, one is 22 degrees. So we consider that when you have this, and then it's also equal to this and also equal to these values. Okay, which is this come up with the ratio of your area of your link divided by your spacing. Okay, so that's when you have to provide your vertical shear reinforcement. Okay, so additional longitudinal force, okay, when using this method of shear design, it is necessary to provide, for the tensile force generated in the tension cord of the assumed truss. So we use truss like a calculation, right, to estimate where is the crack, how to place the shear reinforcement, how to counter the crack so that the force can be acted, and then so that the crack will not happen and so on. And the tensile force in vertical links to be provided in the tensile zone is given by this condition. Okay, so we can assume this force. Okay, so when you assume this force, so basically is this one, when you have the cotangent, is actually equal to FYK multiplied with ASL. So it's actually more or less the same, condition. So to provide this force and tension reinforcement of area ASL working at its full design strength, so must be provided to ensure that this force is developed and or the profile of the stressing tendon may be adjusted to provide greater resistance to the deformation. Okay, so that's the way. So you provide, to ensure that this force is developed, and or your pre-stressing tendons also may be adjusted to provide greater resistance. Okay, just to make sure that it can provide greater resistance to the design shear force. Okay, all right. So this is where we summarize our procedure in terms of the shear check, design shear, either you want to provide or not, and so on. So the first step that you do is actually you calculate the ultimate design shear force, okay, of the beam span, okay, based on your design load and so on. So then at set intervals along the beam span commencing at the section maximum section at the support, follow the step below. The section of the maximum can be taken to be the face of the support where the maximum shear force is VEF. Okay, that will be your maximum shear force, your design, your ultimate. Okay, so then next you have the second step. The second step is whereby you consider where the shear force is not required. So means you provide only the minimum shear reinforcement. So uncracked bending or crack shear is required, uncracked condition. Okay, so if appropriate, the vertical component of the force in any inclined tendon should be taken into account. determine the shear resistance. So if it is required, continue as follows. Otherwise, goes directly to step 5.0. So from here, you will check either you need the reinforcement or not. So if you do not need the reinforcement, means you only provide minimum reinforcement. So you just go straightly to step 5. Okay. So if you need the reinforcement, then you will proceed to step 3. So for step 3, you check the crushing strength, which is the resistance maximum, okay, of the diagonal strut. Okay, like we say, we consider it diagonal, right? So for most cases, the angle diagonal inclination of the strut is theta is equal to 32 degrees Celsius normally, because as we say, when you have free stress, normally it's flattened. It's a bit flattened compared to RC. So with cotangent equal to 2.5 and tangent theta equal to 0.4. So mostly we will have to calculate using this formula. So in step 3, we check, okay, your resistance must always bigger than your maximum shear force. Okay, with theta 22 degrees, with cotangent theta is equal to 2.5. So then if this is the case, then you can go to step 4.0, means the next step. So, but if say that you have your resistance is lesser than your maximum force, maximum shear force, then for your theta is bigger than 22 degrees, you have to calculate your theta. So if theta is bigger, then you have to resize the beam. Okay, you have to resize your beam and increase the concrete strength, or you increase concrete strength, means that instead of using 40, maybe you want to use like 50 and so on. This is what happens when your resistance is lesser than your what you call your shear maximum, your shear force maximum. Okay, and your theta can be calculated by using this lah. Okay, right, let's take a look. Step 4. So in terms of step 4, where you want to you provide, okay, you provide your shear link. Okay, so you provide your shear link by using this, where you have your ASW equal to cross-sectional area, where you consider the legs of the link, which is you have 2 times 2 legs to consider for a single stirrup. Okay, for predominantly UDL, the maximum shear, okay, can be calculated at distance D from a face of support, and the shear reinforcement should continue to the face of the support. So that's the position. So the shear resistance for the link can be calculated by taking the V minimum. Okay, this value will be used together with the shear force envelope to determine the curtailment position of each set of the design links. Okay, so you want to know the curtailment position and so on. So that's why you kind of like use together with the shear force envelope. Okay, so next step, once you provide this, okay, you calculate your minimum link. Okay, this is for for cases where you don't need to provide any shear force, so then you provide your minimum link. This also you have to check against your minimum link. And you have step 6.0, where you calculate additional longitudinal force, either is needed or not. Okay, so this is where you calculate what will be your additional longitudinal tensile force. So the above procedure should be repeated at different sections along the beam. So you have beam span. Probably you might have like different section used along the span. Okay, so in terms of different section used along the span, then you have to consider it by checking one by one. Okay, all right, so I think that's all. Yeah, okay, for example, all right, so we stop here. I think now is almost okay, now it's almost 11:30 a.m. Okay, we're gonna Okay, so I think that's all for me today. So we will continue with the example in our next lecture next week, inshallah. Okay, so in the meantime, any question?
So far no, madam.
No, madam.
No, madam.
All right, so I think if there's no question, I think that's all. Thank you very much. Like I always say, I appreciate you guys for joining me in our online lecture today. So I think so in the meantime, next week, maybe before that, you can go through the lecture, okay, and then try to understand. If you have any question, then we can discuss it further in our next lecture of or else we can also discuss during the on Monday during our 1 hour class, okay. All right, so I think that's all. So I will proceed with the example in our next lecture, inshallah. Okay, so with that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Thank you very much for being here, and I'll be seeing you back next week. Okay.
Thank you, madam.
All right, thank you very much. Assalamualaikum. Take care, everyone. Stay safe.
Thank you, madam.
Thank you.
Madam.
Thank you semua.
Thank you, madam.
Thank you ya semua. New picture everyone next week.
Okay, madam.
Okay.